Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to module 1.5, and in this module I'll extend a little more this basic principle that we have been talking about, how when you have a periodic matrix you can write down its eigenvalues analytically without actually having to go to a computer. And just to recap what we did in the last one, I said that, well, in general, when you have a matrix equation, you could write it in this form. And these H and M's are the basic elements of that H matrix. And as long as like every row looks the same, you can write the solution to these things in the form of an exponential like this. And if you write it in the form of an exponential, you substitute this back in here, and you immediately get the EK relation. So it's like, as soon as I tell you all these H and M's, you could just start from here, this summation over M, this is this summation sign. And what that means is you go to a particular N, and then put in different values of M, and write out all the terms, add them up, and you'll have the EK relation. And we went through some examples. Now, what I want to do, as I said in this module, is explain one important generalization of this principle that's needed. And that's like this. Consider, again, just for simplicity, we'll do a 1D wire for the moment. So you have 1D, but it's not perfectly periodic in the sense you have some things you could call the A atoms and something you could call the B atoms. That's the blacks and the reds. And what happens is A and B are kind of close together, but then the distance from the B to A is a little more. So what that means is if you actually wrote down the matrix, you'll have between A and B, here the connection may be, let's say call it T, but the connection from B to A may not be exactly the same T. It could be something else, T prime, because they are further apart, you see. So when I actually try to write down the matrix, it won't look perfectly periodic, see? That is, what I mean by that is, yeah, let's write the matrix, try to write the matrix, I think you'll see it. So let's say we are trying to write, this is 1, 2, 3, and I've labeled the columns as 1A, 1B, 2A, 2B, 3A, 3B. And on this side, the rows also 1A, 1B, 2A, 2B, 3A, 3B. Okay. And let's say all the diagonal elements are all epsilon anyway. So all these diagonal elements, so this is all epsilon, if you wanted to write it. Now, what about this term here? Well, we are looking at 2A and 2B. So 2A and 2B, they are connected by a T. So I'll put a T there. Similarly, if you look here, it's 2B and 2A, so I'll put a T there. Not a problem. Okay. Now, what about, let's say, this point? You know, this is epsilon T, and this is on this side. And you see, if this was an ordinary 1D thing, I'd have just put T there. But now you see, you have to be careful, because we are talking about the connection between 2A and 1B. So we are talking about this connection, 2A and 1B. So that's the weak connection, the one that's different from the other one. And so what we need to do is put a T prime there. And if you look at 1B and 2A, that's like 1B, 2A, well, same as 2A, 1B, because these connections are always mutual. That is, if this is weak, so is this. So if this is a T prime here, you'll also have a T prime there. And of course, it's a nearest neighbor model, so you still expect this entire matrix to look what you call tridiagonal. There's something down the diagonal element, and then there's something on the upper diagonal, something on the lower diagonal. Only thing is, when you look at the upper diagonal, it's not all T's. It's T's and T primes alternating. So if you went there, it would be a T again, because this would be 1A and 1B. That's that connection. That's T. But then when you go here, so it's like T, T prime, T, then again it will be a T prime, I guess. And you can check. We are talking about the connection between 2B and 3A. So that's the 2b and the 3a. That connection is a t prime. So that's t prime. And then again back to t. Okay? And these are all zeros. This would be t. T prime t. If you wanted to fill it out, you could. Now, the point is then that if you now look at each row, they're really not the same. You see, previously I had argued as long as each row looks the same, you can just write the solution as an exponential. Look at these rows. This is t epsilon t prime, but the next one is t prime epsilon t. And then when you go here, it's again t epsilon t prime, and then it's again t prime epsilon t. If we had continued, I guess we'd see that there would be t prime here, etc. And so, this principle that you can just write down the solution in the form of an exponential won't quite work. If you did that, you'd find it would not give you consistent results. But the way you can make it work, and this requires a conceptual jump here, and that is, you should mentally think of A and B as one unit, as one object. So this whole thing is like one object. So there is this matrix that is, so previously we had an epsilon that was the diagonal element. Now it is sort of like every element is an object, is a two-component object. And so the diagonal element is actually this is this 2 by 2 matrix. And the connection to the left is actually that matrix. And the connection to the right is actually that matrix. See? And once you generalize it this way, the point is, now we are thinking of this as the unit cell. This is your object, connected to that object, connected to that object. And when you think of it that way, it now looks perfectly uniform. Whatever non-uniformity is like what's inside the object. But the object itself is, you look to the right, looks the same as what you see on the right, left. Now if you think of it that way, then the way you generalize it is that this equation that we are writing, when I write psi n, you usually mean the wave function, this component at location n. But now the way you should think of n is this 1, 2, 3, but within let's say n is equal to 2. But within 2, it actually has two components in it. So what that means is this psi n itself is now actually a 2 by 1 column vector. Because it's got two components. There's an A component and a B component. And same with this. This is a two-component thing. It's the A component and a B component. And what's in between is actually a 2 by 2 matrix. Right? So, like we said here, if you looked at psi 2 and psi 2, what's connecting it is a 2 by 2 matrix. So this would be what I'd call H22. This would be what you'd call H21. This is what you'd call H23. See? It's a matrix now, not a number. Now, but now because things look periodic again, now this principle will also work again. You could say psi n is equal to psi 0 e to the power I k dot Rn. Okay? And when you substitute it in there, you'll again get this kind of thing, the same thing. But now you'll have a E psi 0 here and a psi 0 there. Now, we actually had the same thing in the last module also. There was a psi 0 here. But psi 0 then was a number. And so you could just cancel it out. Now you see this is a 2 by 1 column vector. You can't cancel it out. You have to leave it in there. And this then is a matrix, is a 2 by 2 matrix equation. And if you want the energies, you have to take that 2 by 2 matrix and find its eigenvalues. See? This is where this has changed from what we had before. Previously, we just cancelled out psi 0. And this was just a 1 by 1 matrix, which means this is just a number. And then it was a matter of just evaluating it. But now it's going to be a little more complicated. It's this 2 by 2 matrix. So this, I think, will get a little clearer if we just apply it to the problem we were talking about, this one. So let's say we use this idea, and what we want to do is find that matrix. You know, we'll give this a name. Let me write it on top. So this thing here, we'll give it a name H, small h of k, and that's equal to sum over M H n M e to the power I k dot right. And so then the idea is two steps. One is, given the h's, first thing we do is evaluate this 2 by 2 matrix. And once you have that, then the way you find the energy eigenvalues is by solving this 2 by 2 eigenvalue problem. So overall then, two steps. So first thing let's try to do then is, how do we find this h of k? And I have to do this summation over m. And so the idea is, okay, we go to any particular point, let's say this one, and that is the location n. So that's the point 2. We're standing at 2. And then we have to sum over m, and so m could be 2, in which case h and m would be this quantity, or m could be 3, in which case it would be that quantity. M could be 1, in which case it would be this quantity. So basically then, when I try to write h of k here, so I'm trying to write this h of k, it will be a sum of those three matrices. So actually, yeah, let me just separate it out a little bit so you see. So it will be that one plus that one. And similarly, because, as I said, I take n as 2, and then if I put m equal to 2, I get this matrix. If I put m equals 1, I get that matrix. If I put m equals 3, I get that matrix. But I've missed one thing though, and that is, I also have to include the phase factors. Remember, when you go back, when you do this summation, we are putting n is equal to 2, and then we are summing over m 1, 2, 3. That's how you are getting the 3 terms. But of course, to each one, there is a phase factor there. And just like in the previous module, if those two indices are equal, so for the 2 case, the phase factor is just 1, because Rm equals Rn. Whereas when it is 3, that's when we'll have a phase factor. When it's 1, we'll have a phase factor. So this middle matrix, that's the 2, 2, that has no phase factors to go with it. This is it. This one will have a phase factor, and that will be e to the power, let me get a better pen. It will be e to the power I k dot that vector. It's a vector running from this unit cell to that unit cell. And you could run it from the black point to the black point, or the red point to the red point, or from middle, as long as you go from some point in this cell to a corresponding point on that cell. That's fine. So let's say we call that distance, from one unit cell to the other, I'll call it B. Like, I guess previously I had used A for the lattice spacing. I'm just using a different symbol so you remember. It's actually now the distance from one unit cell to the next. So it will be I k dot, if this direction happens to be x, then you'd probably write xb. And this is a 1D problem, so you could just call this kx, or you could just write it as k, just a number, but let's put it kx then. So it will be e to the power I kx b. And plus, because you see that phase factor here, as I've mentioned before in the last module, it's the vector that runs from point n to point m. So in this case, it's the vector that runs from 2 to 3. So it's that vector. So that's the positive one. On the other hand, when I'm writing this one, that's when it's run from this one to this way. And so you'll have a e to the power minus I kx b. So the overall H matrix then is this plus this times the phase factor, that times the phase factor. So let's now, we can combine all this to obtain a 2 by 2 matrix. So this h of k overall would look like, if you look at the diagonal elements, it's just epsilon, epsilon. It's 0 here, 0 there. So when I add it up, it's still just epsilon, just epsilon. Now if you look on this one, then you see a t, and then you see t prime, this. So it is t plus t prime e to the power minus ikx b. And if you look at this corner, it's t plus t prime e to the power plus ikx b. So this is this H matrix, this small h of k. And I get, yes, this kx basically. And if we want the actual energy eigenvalues, then what we need to do is write down the eigenvalues of that matrix. See? And this is where, I guess, let me just state something which you can easily check. And that is, if you have a 2 by 2 matrix, something looking like this, say epsilon, epsilon, and you have some quantity here, let's call it, say, h, h0. I guess I call the whole matrix h, so I'll call that h0. And these matrices will usually all come out Hermitian in the sense that it is equal to its conjugate transpose. And so what you see here will be the complex conjugate of what you see there. So if this is h0, this will be h0 star. And the point is, as long as these two diagonal elements are equal, the eigenvalues of that matrix are given by epsilon plus minus magnitude of h0. That's it. So in this case then, you could write the eigenvalues. Write this eigenvalues of this as epsilon plus minus magnitude of this. Magnitude of that complex quantity. So plus minus, so it means if I'm plotting this, E versus kx. So for every value of kx, I'll get two energy eigenvalues, one the plus sign and one the minus sign. So you could draw a line here, that's like your epsilon line, and then you'll have something above it, something below it, this plus and minus. And so you'll get these two branches to this curve, which might look something like this. So for every k, there are two eigenvalues. Every k, there are two eigenvalues. And so previously, when you had the uniform 1D thing, when you plotted E versus k, there was just one branch, whereas now it is two branches. And in general, of course, band structures usually have many branches. Why? Because, you see, what we did here, I took off this picture, so let me just draw it again. What we did here was I considered a wire with two atoms to a unit cell. So the unit cell kind of had these two things to it. And in general, you see, it may not be two, it could be a whole lot more. It could be 20 of them, for example. If it's 20 of them, then when you write down this matrix H of k, you'd have a 20 by 20 matrix. What that means is for each k, you could have 20 branches. So if you actually look at a band structure in a textbook, you'd often see lots of branches running all over, you see? And can get quite confusing. I mean, it takes a while to actually see what is happening. And so it's always useful to do these simple problems to make sure you know what you're looking at. So here, to go further, we'd have to find the magnitude of this. And one of the homework problems is designed to give you some practice with this, and I'll go over it in the tutorial. I believe it's the third one, tutorial 1.3. And what's instructive to do is, you see, I said that you needed this method of going to this 2 by 2 because this connection happened to be like t, and the next one happened to be t prime. Now, what if t were equal to t prime? Of course, I could still use whatever method I've used here. Now, whatever I did, I could just set t prime equals t. But then, I'm really solving the problem from the last module, because if t is equal to t prime, then it's really just one uniform wire. Only thing is, right now the period is b, that distance, whereas if it's one uniform wire, the period would be like a. It would be that distance. So if t is equal to t prime, you should get back what you had in module 1.3. And that's kind of what I ask you to check in this homework problem 1.3, and in the tutorial, I'll go over that. That is how, starting from here and putting t equals t prime, you can actually get answers that correspond exactly with what you did in module 1 in the last module, although the details look a little different, but they're really not. It's the same thing.